Welcome back, folks. Series, parallel, neither, both. We talked about series. Let's talk about parallel. And then once we have series and parallel right, then we can talk about neither and both. So let's make this video be about parallel resistors. Let's get the Blackboard back up here. Not that horrible software they make us occasionally use. But like the old-fashioned Blackboard that I started teaching on with chalk. I miss chalk. Okay, parallel. Two elements are in parallel. This is the other way to connect things. Elements are in parallel. If, and here we go, they share the same two nodes. Okay, so you have to look at what nodes each component is connected to, and they have to have the same two nodes on either side. Okay, so let's draw a simple case of that, and we can say we have a node here, and let's connect a resistor there and a resistor there. So both of those resistors are connected to that top node, and let's connect them together down here on the bottom node. We'll call that A, and we'll call that B. And here's R1 for this schematic and R2 for this one. Okay, these are in parallel. They share the same two nodes. R1 is connected to A and B, and R2 is connected to A and B. All right, so I want you to ask yourselves these questions when we're looking at whether things are in series or in parallel. Do they share a node exclusively, and are they connected to the same two nodes? Before you can do that, you have to be able to identify the nodes, so hopefully you've gotten good practice doing that. These two can be combined together. Okay, we can combine them together this way. We can say, well, between A and B, we have one resistor. We have an equivalent resistor. But when they're in parallel, we're making two paths for the cars to drive down now, right? So the resistance should actually go down. Should be easier for charge to move through this circuit since they're in parallel. There's two different paths for it to travel in. Two different branches, if you will. So when they're in parallel, the conductances add. And this is why we had to introduce conductance earlier in the course. When in parallel. Okay, so if the conductances are going to add, okay, and we want to get to RAB ultimately, we have to remember that the conductance of the first one, so it's going to be the conductance of this resistor here, is the inverse, right? So it's going to be 1 over R1, and the conductance of the second one is 1 over R2. All right, when they add, ready? GAB, so the conductance of our equivalent one up here is going to be 1 over RAB, and it's simply going to be G1 plus G2. Okay, so the conductance of the combination is equal to the individual conductances added together. So in order to do that, we're going to just substitute these down here and say 1 over R1 plus 1 over R2. Okay, so there's two forms that you're going to see this in. I used to strictly prefer one form, and then I started teaching and I realized it makes teaching a little faster. So we take this and we're really after this resistance. We got to solve for this here. So let's say solve for RAB. Okay, and we have these two inverted resistances over here. There's one that you're going to see in textbooks a lot. Some of you probably know it, and we can do that by multiplying, getting this over a common denominator, flipping some stuff around, and it ends up being R1 times R2 over R1 plus R2. Okay, so we might call this the product over sum form. Okay, it has a limitation, has a really important limitation, and I find it gets left out and it doesn't get emphasized, and then when you start putting more things in parallel, you get in trouble and you don't think about this limitation. So I want you to be aware of it. It wasn't emphasized for me. I'm going to emphasize it for you. I expect better of you. You have a much better teacher. I shouldn't say that. I had good teachers. So product over sum form. The other form, the limitation over here is that only works for two resistors. Okay, if you have three things in parallel, you're going to be very tempted to take all three. So let's draw three things in parallel. Look at these three. They're all connected to the same two nodes. They're all in parallel with each other. Okay, we call this R1, R2, R3. You're going to be really tempted to go, I know, let's call this C and D. I know what to do with this. The resistance between C and D is R1, R2, R3 over R1 plus R2 plus R3. Go back and talk to your algebra teacher because you should get your money back. Don't do this. Okay? Bad. Bad, bad, bad. Not mathematically equivalent. What you're really doing is adding conductances. And combining those fractions isn't going to work out that way. But it's a sloppy thing that a lot of students do. So I want to say it. I want to point it out. Don't do it. If you have three or more, you can use the other form. And if you have two, you can use this other form. And that's why I used to prefer it. But for derivations, the product over sum works pretty well. For three or more, we have to say 1 over RCD is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And then we again want to solve for the resistance, the equivalent resistance here. And we can just say 1 over R1 plus 1 over R2 plus 1 over R3. This is mathematically okay. Don't break the rules. Okay, and that includes everything with math. If we have more, we can just tack them on to that sum in the denominator. And it kind of expands a little more nicely that way. So you'll see both forms. I'll use both forms. But I want you to know that the product over sum form has a limitation. This form over here doesn't have a limitation. You just add more terms to the denominator and you're going to be okay. Okay, let's see. The other thing I'll caution you about, and the other misconception that I have to fight long and hard about, is things that are electrically in parallel don't necessarily have to be geometrically in parallel. They're two different meanings. Electrically in parallel is different than geometrically in parallel. This is an important one. Okay, it's important because look at these two resistors and how they're connected. They are not geometrically in parallel, but they are electrically in parallel. There's only two nodes in this little circuit. It's not doing much. There's nothing to push current. Okay, but the two nodes here are here and here. So both resistors are connected to the red and the blue node. Okay. So they are electrically in parallel. But clearly they're not geometrically in parallel. Okay, I can play other games as I love to do. Let's see. Oops, that is the wrong color. Not what I was going for. Okay, so if I have 3 resistors, these two are not in parallel as far as I'm concerned. I don't care how you draw them. Okay, they are geometrically in parallel, but we don't care about that. They're not electrically in parallel because they're not connected to the same 2 nodes. Okay. So we have 3 nodes in this circuit. That yellow doesn't show up against the orange that well. These are the life choices I make. Okay. This one's connected to the blue and the purple. This one's connected to the yellow and the purple. They don't share the same 2 nodes. Ask yourself that question. Whenever you go, oh, those are in parallel, stop and ask yourself that question. That way you're not going to screw it up. Okay, so geometrically in parallel does not mean electrically in parallel. How are those 2 connected? That one and that one. Series, parallel, neither, both. Okay, you got to ask yourself all of those questions. Let's move to the next video to do that so that we can see examples of all of these things. Okay, stay tuned and good luck, folks. But wait, there's more. All right, I forgot an important thing. So I'm going to tack this on. Sorry for the hard cut there at the end. When things are in parallel, since they're connected to the same 2 nodes, let's get an example of when they are. There's only 2 nodes in the circuit, so there can only be one difference in energy. The difference in energy from the blue node to the red node across this resistor is the same as the difference in energy from the blue node to the red node across this resistor. So when 2 things are in parallel, and this is important, when 2 elements are in parallel, they have the same voltage. Okay, when they're in series, they have the same current. When they're in parallel, they have the same voltage. Important enough that I made another video and I'm going to glue them together and do all the stuff. Okay, but I do want to talk about it in coming videos as it's kind of a key concept. How did I miss that? Okay, this time, for real. Stay tuned and good luck.